Welcome to another Shock and Vibration webinar. My name is Tom Irvine and I'm the instructor for this unit. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for sponsoring this series of webinars. And today we're going to be talking about sine filtering. We've actually somewhat covered this before. Parts of this we've covered before, but we're going to do put some new twists on an old topic. So previously we did some time domain sine curve fitting for signal identification. It's particularly useful for identifying frequencies. For example, we took a look at a tuning fork and identified its frequency in one of the very first units. But another situation has come up. This is at a request of someone who sent me an email, and he needed to take some sine on random data and separate the sine from the random components of that signal. And so I realized that that was easily done, or readily done, and we could just take our curve fitting method we've used before with random number generation and some trial and error, and it has some built-in convergence and least squares routine built into it. And we could identify the sinusoidal tones and then subtract them from the broadband random data, thereby separating the two signal types. And one of the things that I've realized that if we have, for example, measured data, if we have measured data that is sinusoidal or maybe sine on random, those sinusoids do not have a absolutely constant frequency, neither do they have an absolutely constant amplitude. Just due to the practical real-world physics, there'll be some slight variation in the amplitude envelope and some slight frequency variation. So anytime we're doing some sinusoidal curve fitting, or we're trying to do some curve fitting for some sinusoidal data that's measured data, we probably will need to have more than one sinusoids at or near the frequency of interest to match the data. And you'll see that in an example coming up. The example we're going to cover today works best for short time segments. If you have 60 seconds worth of data sampled at 100,000 samples per second, this is not the method to use, but it works for shorter time segments. Of course, that depends on sample rate as well. And one of the uses, in fact, the first use I had for this method was many years ago, and at one time I had an opportunity to work with quite a bit of measured data, and this would be test data, ground test data, and it was somewhat common that we would get, or occasionally we get some 60 hertz noise, or some other noise frequencies would come through. When we were back in the old days when we recorded data on magnetic tape, for example. And there's many ways that noise can get into signals. Perhaps this is more of a problem in the past than is so today, but there's clearly a potential even today. There could be electromagnetic interference, for example. Ground loops can occur. If there's a test with multiple power cables and other sensor cables, and those cables are bundled together, that can be induced eddy currents or crosstalk, or just some sort of electromagnetic interference. So you may perhaps potentially have a need to remove some spurious noise signals, sinusoidal noise signals from your data, or you just may have some data that is free from spurious noise, but it does have a sine on random characteristic, and for your own purposes, you might want to separate out the random and the sine components. One hypothetical example I can come up with for launch vehicles is that, say for example, there's a family of launch vehicles, each has the same solid rocket motor for the first stage, and this particular solid rocket motor has a thrust oscillation in the internal motor cavity, and maybe this particular type of vehicle, I'll call it this particular model, different serial numbers of that model will fly on a series of flights, but each will have a different trajectory. and the external random vibration generated from the, I should say the random vibration generated from the external flow may vary from flight to flight depending on the trajectory and the transonic and alpha Q conditions and at what altitude do those occur and so on. So in that case, there may be a particular desire to pull off the sine data from each of those flights to see how the motor's thrust oscillation induced vibration varied from flight to flight apart from the random data. That's just sort of a kind of a hypothetical example, but you kind of get the idea. So the first exercise we're going to do is just going to be using our own made up or synthesized data, and we do this because we want to develop confidence in our tool, in our methodology. And you'll see this here shortly. We're going to do an example where we kind of go full circle, and you'll see what I mean as we go along. So let's type in vibration data, and this week we're up to version 7.3 and rising. And we're going to do a review exercise. We've done this before where we generate a signal, and we're going to generate a white noise signal as we've done before. And I'm just going to scan over what the 10-second duration, standard deviation 1, 10,000 samples per second, and we're going to low pass filter at 1,000 Hertz and save it as white. So how well do I remember all those numbers? Let's see. So let's go ahead and generate the white noise. We in the first couple of webinars, this was a common exercise. We haven't done it so much lately. Okay, here's our histogram of the instantaneous acceleration time history, and it's a nice pleasing bell-shaped curve. Here's our band-limited white noise, and we save this as white. And if we zoom in, you should say that yes, indeed, it is random vibration. So random vibration. Doesn't look like there's any particular sinusoids embedded in that data. Now the next thing we're going to do is kind of a new exercise for today. We're going to add sine tones to the existing signal. So here we go down to this bottom here. And let's see, I think we're going to do like a 100 Hertz amplitude 1. So now I'm going to push this calculate button. This is not, we will not actually do the calculation at this point. Rather, this just opens up another dialog GUI. So this is vibration data underscore add underscore sine underscore tones. The input array must have 2 columns, time in seconds and amplitude. And for this exercise, it doesn't matter what our amplitude unit is. We'll just say we have some amplitude, and that's the white noise. We have to read that in. Actually, I'm going to click on other here. Let's read that in. Okay, so we've just read in our white noise, and we're going to say other. If we had chosen the acceleration, then the function would have gone through a routine where it produced a sign on random that had 0 net displacement and 0 net velocity, but we're not going to worry about that for today. So let's add 100 Hertz amplitude 1 sinusoid to that signal, and we're going to, the output name is going to be combined. It's going to be the combined sine on random. Let's calculate. This will actually, okay, now we've done the calculation. The histogram, it still kind of looks like a bell curve, but it's a little bit departing from the bell curve ideal, just a little bit. Here's a combined sine on random. Let's zoom in, take a close-up view. Now you can kind of see there's something kind of periodic buried in that random data. And if we counted the peaks, and I know the peaks are kind of ambiguous, but if we counted what we might call the major peaks, whatever that means, and divide by time, we would see, yeah, it kind of looks like there might be a 100 Hertz sine signal embedded in that combined signal. Okay, we have to push the save button to save it. Okay, now it's officially saved. So the next thing we're going to do is let's take a power spectral density of this combined data. We'll see what that looks like. We've done PSDs before many times. Okay, so this script calculates the power spectral density of a time history. The input array must have two columns, time in seconds and amplitude. Combined, view processing options. Now actually the PSD format is not the best format to characterize a sine signal. We've talked about that before, but let's go ahead and, there's the usual trade-off between degrees of freedom and delta F. We ideally would like a high degrees of freedom, but a low delta F, and we're not going to get that. That's not how the mathematics work out. So let's do case number 3 here and just kind of take a quick look at this PSD. And you can see, oh, okay, we've got this PSD. It's kind of a sort of a white noise, band limited, so there's a roll-off. And that, yes, there is a spectral peak there at 100 hertz. This is a, okay, this actually says G squared per hertz. We're not actually going to worry about what the units are. But this is our 100 hertz spectral peak for our sine on random showing up in that data. So the next task is going to be, what do we want to do next? We'll skip over cumulative RMS. So I probably should have just made that other and cleared out the unit, but you get the idea. We could also, just for curiosity, take an FFT of that same data, and an FFT is more suitable for sine. So I do combined. I think we can get away without putting in the Y label and the max frequency. See if we can get away with that. Yeah. So here you can see the 100 hertz peak. Maybe we ought to go back and put a plot maximum frequency of 1,000. See that peak a little better. So we get a peak. In this case, it's an FFT, and the way the delta F parameter works out. Anyways, our 100 hertz spectral peak is showing up at 99.95 hertz, and that's close enough. That's looking good. So our sine on random signal, we've looked at its PSD, we've looked at its FFT. We kind of went through that a bit quickly, so you might want to go back and do this as a homework exercise. Take your time a little bit. Okay, now what we're going to do is we're going to go to time history, and I put our new function for today under filters various. Now what we're doing is very similar to a pre-existing function called sine and damp sine curve fit. And this previous function, the frequency detection is automatic, whereas the one we're going to do is going to be a manual frequency entry. And you'll see what that means as we do the exercise. Otherwise, there's similarities. So we have our various filter options here. We've already covered Butterworth filter. One of these days we'll get around to Bessel filters. Mean filters, I think we talked a little bit about those once upon a time. But today we're going to remove the sine tones. And actually it's going to be, remove sine tones is not the best way to describe it. We're actually going to separate the sine tones from the background signal, which is a broadband random white noise background. So the input array must have two columns, time in seconds and amplitude. Let's type in combined. Now we know what we already have done our FFT, our PSD, and even from our, obviously from our synthesis, we know that we have a spectral peak at 100 hertz. The bandwidth allows for a little bit variation, and it's kind of a plus and minus. Actually, you take the bandwidth and take 1/2 of the bandwidth, and that's going to be a plus and minus about this nominal frequency, and that's for establishing the frequency limits across which, or inside which the MATLAB script will look for the frequency when it does its random number generated and curve fitting with the convergence and the least squares and all that. So let's just type in, well, we'll type in 2 hertz. That means we're going to be looking from 99 to 101 hertz. And we're only going to look for one 100 hertz component. And let's go ahead and we've got to plot the input now. Got 10 seconds. I guess we can do the whole 10 seconds. So let's do take the whole 10 seconds and do a curve fit to extract that sine. We're going to separate the sine and the random. So let's go ahead and calculate. So numbers scroll by, and the calculation's already done. Okay, one thing I kind of messed up here. I already had an existing figure 3. Okay, let's just redo this. It doesn't take very long. Sometimes when you're using my software, you have to manually close out previous figures. Okay. So what do we have here? Now the blue curve here, our input data, this is whatever amplitude it might be versus time. The blue curve is the combined sine on random data. The red curve here is the synthesis, and that's just the pure sine component. So let's kind of zoom in here and see what that means. So you can kind of see that that blue curve, kind of sort of see it. It has the 100 Hertz component embedded inside, and the red curve is trying to model that 100 Hertz behavior inside that signal. Now we should also look down and see these results here. So the results here in the command window show that the MATLAB's function found a sine component with an amplitude very nearly equal to 1 and a frequency very nearly equal to 1. We'll ignore the phase angle. That doesn't matter to us. So what this is saying is, well, we already knew there was an amplitude 1 unit, 100 Hertz signal embedded in the sine on random combined signal. We already knew that. We haven't learned anything new. But what we have done is develop confidence in this tool, that this tool can be used for separating out the sine and the random portions in this case. So what else can we do here? We've got some options. Okay, the synthesis in this case will be the sine function that we found. The residual will be our input data minus that synthesis. So let's we'll go ahead and save both of those. I'm going to save residual as residual, and I'm going to save synthesis. I could save it as synthesis. I'm just going to call it sine. So those are two arrays that are now in MATLAB workspace. And if we want to get more details on what those signals are all about, we can go to statistics. And let's call in our first one, which was, we'll call in the residual first. So the residual is the combined sine on random minus the sine. So it really will just be our original white noise, the very first thing we generated. So this is our original white noise. And as we scroll in, we can see, yeah, it's random vibration, but it doesn't look like there's any prominent 100 Hertz signal there anymore. I suppose if we wanted to be extra careful and verify it, we could do a PSD of residual, and I'll let you do that for a homework exercise. Then we also have the sine function by itself. Sine function by itself has a bathtub histogram. That makes sense. Well defined. And here is the amplitude 100 Hertz sine function that was extracted from the sine on random or combined signal. So that's all working out well and good. So now we've done this little case with our made up data and seemed to work out pretty good there. So what if we have some real world data, not just made up data? So what are we going to do? Well, first we're going to go back to the slides, and we're probably going to see some screenshots from when I did this when I was preparing this webinar unit. There was our sine on random histogram, not quite a bell curve, but pretty close. Then we did the remove sine tones function. We went and processed, calculation, whatever you want to call it. This was the comparison. The numbers here are just a little bit different than I demonstrated in class, just due to the way MATLAB has its random number seed. And this was a close-up comparison. You can see, and this is a slide, PowerPoint slide version. The input data is the sine on random data, and that's the blue curve, and the red curve is our synthesis, which is really just one sine function at 100 Hertz. Then the residual is the original data minus the sine synthesis. Okay, let's go back. I think we probably took a look at this piece of data once before, but some time ago I flew in an aircraft similar to the one shown here. It was a Bombardier Q400 turboprop aircraft, and I was a passenger in the cabin, and I just so happened to have a seat that was pretty close that I could look right out and see the propeller there. So this aircraft, it has two Pratt & Whitney 150A engines, and the engine propeller rotation rate during takeoff and climb is 1020 RPM. That is throttled back at cruise altitude to 850 RPM or 14.17 Hertz. Now there are 6 blades on each engine, so the blade passing frequency is 85 Hertz. So what I did is I made an audio recording while riding as a passenger inside the fuselage, and those engines create quite a bit of noise, particularly at the fundamental blade passing frequency at 85 Hertz, but also at integer harmonics of 85 Hertz. And of course, as I made my recording, that sound was being partially attenuated by the fuselage walls, but I still was able to get a really good recording. Let's go ahead and call in this data. I'll show you what we're going to do with it here. And this is one I've added to the library. So if we go to import data to MATLAB, and I probably have changed this around since you saw it last. You can always just load your own data into MATLAB. That could be an external ASCII file, a MAT file, and then we have all these different library functions here in the center and right hand side. And today we're going to take this acoustic time history data. This will be uncalibrated sound pressure versus time from the Q400 turboprop aircraft. So we've got time in seconds and unscaled sound pressure. This will be called Q400. And we'll do a couple things with that. Okay. So what should we do? We could go to statistics, for example, and call in Q400. I'm going to skip over the y-axis label. Skip over absolute peak distribution, skip over cumulative histogram. Kind of odd histogram there. Okay, so here's this time history. This is the sound pressure time history with uncalibrated units for the y-axis. And we zoom in a couple of times, we can see kind of looks like something periodic going on. In fact, there is something periodic. We'll skip over the esoteric statistics. Let's take this file and let's do an FFT. We'll get a preliminary idea what the frequencies are. Well, actually, you'll see it at 85 Hertz and integer multiples thereof. So we've done FFTs many times before. Rectangular window. Okay, let's go to this one here. So this is the Fourier transform, and the y-axis, it's actually peak pressure, but we don't know what the scale factor is, so we'll just call it peak pressure versus frequency in Hertz. And here you can see, and this spectral peak at this dominant one, we call it the fundamental if you like, is at 85 Hertz. Well, that's the blade passing frequency. Now take 85 and multiply by 2, and that's the second peak at 170. Then multiply by 3, take 85 by 3, that's 255 Hertz. So you can see there's evenly spaced spectral peaks, and you call these the harmonics or the integer multiples. There is an overall tendency for the amplitude of these harmonics to decrease as frequency goes on. And again, we have to take into account that the fuselage wall of that aircraft is probably much more efficient at attenuating the higher frequencies than it is the lower frequencies. So if we had an external microphone, that would have been interesting to do a comparison, and we could have calculated the transmission loss through the fuselage walls, but we're not going to go that far today because we only have the one set of data. Okay, so our task is going to be to extract the 85 Hertz component and its harmonics so we can see what's left over in the signal. So who knows why? For some reason we wanted to take out all those harmonics, yeah, as well as the fundamental frequency. So let's go to time history. We'll go to filters various. We're going to remove sine tones. Okay, now our file from that aircraft is Q400, the sound file. And let's just start off by removing the 85 hertz by itself. Let's start off kind of simple. So 85 hertz, I'm calling it the fundamental. You can call it the blade passing frequency or fundamental blade passing frequency. I'll just give it a little bit of margin here. That's going to be equivalent to 85 hertz plus and minus 2.5 hertz. Now again, that 85 hertz is not going to be a pure textbook steady state 85 hertz. There's going to be a little bit of variation in the amplitude, a little bit of variation in the frequency, just due to what I call the law of practical physics. So it's probably not good enough just to extract one 85 hertz. So let's extract, say, 12 85 hertz components. Okay, so let's see, we've got to plot the input. That's our next thing we've got to do. This is the sound pressure versus time. We're not going to do the whole signal. It'd take too long, so let's just pick from 5 to 10 seconds. Let's just, if we had more time, maybe we could do the whole signal or whatever, but just for brevity, let's only do a 5-second duration. And let's calculate. See what happens. So I've got numbers scrolling. You can actually, I should put these where you can see them. This is just showing as the software identifies new best cases for each of the 12 sine tone cases. Okay. Anyways, what we found is we found a series of 10 components at or near 85 hertz, and the first component we identify has the highest amplitude, 0.5 amplitude. Now thereafter, as we try to identify additional sinusoids near 85 hertz, we see there's a somewhat of a trend of diminishing returns. So we could have, gone on and done some arbitrarily high number of sinusoids. In this case, we just did 12. Let me just do that over again, because I've got to learn to be a little bit more organized and go back and fix my software so it closes out the old plots for it, brings in the new. Okay, redo. One of the neat things about, everyone has a smartphone today, right? You have an iPhone or a Samsung or whatever, Samsung Galaxy, whatever you might have, and these smartphones now have apps for doing sound recording. And the airlines have recently kind of eased up on their rules for having electronic components turned on in flight, so you can actually take recordings of takeoff, cruise, and landing if you're flying as a passenger in an aircraft. Now, a little bit of caveat there. It depends on the type of aircraft. It depends on what kind of engines, whether they're turbofan or turboprop, the engine models. It depends on where you sit in the aircraft. There's some aircraft flights where I've tried to make recordings and the results were just kind of boring. but other times, particularly for smaller aircraft and particularly if it's a turboprop, you can get some pretty interesting recordings. Okay, here's a better view of these 12 sinusoids, all about 85 hertz, and you can see how the blue curve, which is the measured data, compares to what's happening at 85 hertz. So obviously what happens at 85 hertz is a good portion of that input data, but there's obviously other periodic things going on with that data, and those other things going on with that data, that's due to the effect of harmonics. So I'll show you, and here's the residual. This is, okay, what if you take that sound data and just subtract out that 85 hertz? So what's left is everything other than 85 hertz. I'm speaking ideally, of course. But what's left still has some periodic things going on. So let's say we're going to be a little more aggressive. And I've got a little button here. I'll show you how this works. Let's do 8 tones altogether. And we're going to set our first tone to have 85 hertz. That's the fundamental blade passing frequency. And it's so often that we are looking for integer harmonics. I just have a click on integer harmonics thing. So you can see we have each number is 85 hertz higher than the higher row. So 85 plus 85 is 170, plus 85 is 255, and then so on. So these are the fundamental and the it's integer harmonics, or whatever you want to call them. Maybe overtones if we were talking about music, although I have to double check on overtones whether they need to be an octave or whether they can be integer multiples. Okay, so bandwidths, and probably as we go to higher frequencies we ought to increase the bandwidth a little bit. And we'll do 12 again for the 85 hertz, and then the higher harmonics, probably a little bit easier to characterize them because they weren't quite so active as was the 85 hertz. But I'll just please go through this as a homework exercise and make up your own numbers or whatever. Okay, everything else looks good there. So let's calculate, and now we're trying to take out the fundamental plus the next 7 harmonics for a total of 8 frequencies. Now, the total number, if we were imagine taking these numbers and copy and paste into Excel spreadsheet. If we sum up this column here, that's the total number of sinusoids we're looking for. But they're clustered around 8 frequencies, which in this case happen to be a fundamental with its integer harmonics. Let's see, looks like we're about partway through. I'll go on to some slides while we're waiting here. Okay, so this is the turboprop aircraft, which is excellent type of aircraft for making acoustic recordings. And we called in the Q400 data. We took an FFT. Now, I'm going to give you a little sneak preview of what's going to happen. We are taking out this fundamental and its integer harmonics. But there's other things going on with the data. Like there's some other little peaks here. Like here's one. Here's another one. Okay, here's the... Looks like our data is finished. So the bottom line is that there's going to still be some other little sinusoidal things we didn't get around to taking out yet that will be in the residual data. So let's kind of go and see how well we did here. So you're going to see we have a good matchup but not perfect. So I call that good but not perfect. Well, mostly it's not perfect because even though we take out the main sine tones, there's still these other little minor sine tones that are entering into the data, as well as some background random vibration as well. So let's see, here's the residual. Let's go ahead to, let's save this. So we're going to save this. I'm going to save the synthesis again as sine, so we're going to overwrite the previous file. And the residual, let's call that residual again. We'll overwrite the previous one. Okay, now our peak here is 354 hertz. This is the residual. So this is the recording I made minus 85 hertz and its integer harmonics. So what is 354 hertz? Is that some 85 hertz harmonic that we just missed? Well, let's do 354.2 divided by 85. Let's see if that's an integer. No, it's not an integer. It's about 4.2. So if we go back to the FFT of the, let's go make this full scale here. So see that little peak right there? That's what's popping up as we take an FFT. So that is not an integer harmonic. We could go back and we could tell the program to take out the 354 hertz component, but we'll skip over that for now. But you kind of get the idea. This is a tool here that you can use to separate out the sine and random components if you would have such a need. And even if you never have a need, it's just kind of a fun little exercise to run through. Kind of covered this before. In this case, I just show the first 10 components of a curve fit run I did with each of the components at or near 85 hertz, corresponding amplitudes with a bit of diminishing returns effects. Here was the comparison, the slide version of the input data and the synthesis. There was the residual, that's the original data, original measured data, minus the synthesis, which is a collection of sine functions. And here we took the FFT and we found that we had a leftover peak at 354 hertz. Now what was that due to? Well, it was unrelated to the blade passing frequency. Who knows what it was due to? It could have been some cabin noise due to some air ventilation system, or it could even have originated in the engine, because the engine has other frequencies besides the blade passing frequencies. Who knows? Okay, that's all for now. Always as I do this, I think of, oh yeah, there's a couple of different ways I can make this thing better. Make the software a little bit more user-friendly, and so we don't have plots superimposing on each other. But I'll just take that for my action item. And that's all for now, and hope you've enjoyed this webinar, and send me an email sometime. So thanks and goodbye for now.